I am pretty good, actually.
Oh, the hat again.
Hmm?
You're wearing the hat again.
Yep, still haven't. Actually, I booked an appointment to get a haircut this weekend, so
Oh,
yeah, there's that. Probably will still wear the hat afterwards, but it doesn't matter at this point.
it's a nice hat.
It's just a regular white hat. There's nothing on it.
Really? It
Yeah.
looks like lavender blue
Oh, is
on
it?
screen.
Okay,
But
then
it
that's
looks like
probably
a
just the
pastel
camera.
color.
Hmm?
It looked like a pastel color. It looked pretty good.
It's just a plain white hat.
Well,
Okay, but
now we
yeah, I'm glad you guys like it. All right, so last time we finished a topic, partial fractions. So um, again, our normal schedule. Does anyone want to go over any questions from the homework? Question 2, I can't type a fifth term for decomposition. All right, let's see what that is. Okay, so I have copied and pasted question 2. This is what it is on my version. Is it similar to what you have as well? Yeah. Okay, so what's the issue again? So you say you can't type the fifth term. Um, oh, I see. Yeah. I actually have gotten emails from a couple of other students about the issue as well. So yeah, don't worry about that. Just send me an email and then I'll just manually give you the credit for this question. It's been happening to some other students as well, so don't worry about it. Okay, so besides that question, anyone else have anything they want to go over? Question 5. All right. Screen, paste. Is this question 5? Yep. Okay. Sure, let's try this one. So evaluate the integral, and this is partial fractions. So first things first, do we need to do long division here? Right, we do not, because the degree in the numerator is less than the degree in the denominator, so we don't need to do long division. We can just go straight to partial fractions. Before we start, we have to factor the denominator, so let's do that. This is x, and then you'll be left with x squared minus 1, which is x minus 1, x plus 1, right? Okay, so there's your denominator factored, which means we need 3 fractions when we split it up. So we will have one for x, one for x minus 1, another one for x plus 1. Okay, and then were you able to get the numerators for these 3 fractions? Like solving for a, b, and c. Were you able to do that part? Okay. So let's see if we can figure it out then. So this is a, this is b, and then this is c. You didn't know how to do the roots. Yeah, we can go over that. So when we take our 3 separate fractions and we try to get common denominators, that'll give you the following equation. So you will have a times x minus 1, x plus 1, plus b times x plus 1, plus c times x times x minus 1. Yeah, and this is equal to our original numerator, plus 2x minus 7. Okay, so you want to use convenient values of x, which are the roots, in order to solve for a, b, and c. So do you know what the roots would be here? So they're basically x values that would set one of your factors equal to 0. So for example, you have a factor here, you have a factor here, these are all factors. And then, yeah, you choose values of x that will make those parentheses go to 0. So one good value is to let x equal 1. If you do that, then this whole term will go to 0 because the x minus 1 goes to 0. So you will have 0a plus b times 1 times 2. So that's 2b. This term will also go to 0, right? Because there's an x minus 1 there. So you just have 2b is equal to 7 plus 2 minus 7. So that's 2. So this leaves you with b equals 1. Okay, and then what's another good value of x we can use? 0, yeah. So let x equals 0. That will cancel out everything except for the first term, right? So that will leave you with negative 1a is equal to 7 minus 2 minus 7 minus 2. So a equals 2. I think that's right. Okay, and then what's another value of x we can use? Yeah, -1. Because that will cancel out everything except for the last term, right? Because -1 cancels out this factor as well as this factor. So we have c times -1 times -2, so that's +2. So 2c is equal to actually, wait, did I do the x equals 0 one correctly? When x equals 0, we have negative a is equal to, sorry, I made a mistake here. This is not right. This is -1a is equal to -7. So a is 7. Okay. So when x is equal to -1, we have 2c is equal to 2. So c is 1. Is that right? I don't know. I feel like I made a mistake somewhere. Okay, let me just double check x equals 1. So that goes away. That goes away. We have 2b is equal to 7 plus 2 minus 7. I don't know. I feel like I made a mistake somewhere. I don't know. I can't find it. But you solve for a, b, and c like that. And then once you have a, b, and c, you can go back to your integral, and then you fill in what a, b, and c are. So 7, 1, and 1. So you have 7, 1, and 1. So when you integrate this, you will get 7 ln of x plus 1 ln of x minus 1 plus 1 ln of x plus 1. So does that look like the answer? Yeah, I mean, our answer, you can just use the laws of logarithms to combine these into a single logarithm. Yeah, I think we did make a mistake because this one is in a denominator, so c was probably a -1. Yeah, we probably made a mistake somewhere, but I mean, you get the point. All right. Anything else? Question 10. Let's see. So here's question 10. All right. So for this one, do we need to do a long division? Actually, you don't, because the degree on top is 3, and the degree on the bottom is 4, because you have x squared times x squared. So yeah. So the degree on top is less than the degree on the bottom. So this is similar to the last one. You just factor the denominator. Well, they already factored it for you, so you don't need to do that. You can just go ahead and go straight into the decomposition. So you have x squared plus 1 as one fraction, and then x squared plus 7 as the other one. So because these are both quadratics, your numerators will actually be linear. So it's ax plus b, and then cx plus d. And then this one, I think, will probably get quite involved with like solving for a, b, c, and d. Like you'll have to do it the hard way, which is like not using the roots because I don't think these have roots. But what was the confusion with this problem? Because I can't do this whole problem out like fully because that'll take too long. You couldn't, is it solving for a, b, c, and d? Okay, well, the general idea is that you're gonna have this equation. So you have ax plus b in parentheses times x squared plus 7 plus the other numerator times x squared plus 1 is equal to 7x to the third plus 6x squared plus 49x plus 6. Yeah, you can't really use roots here because there's no value of x that'll make anything go to 0. So this one's long. So I would probably just recommend you just to like plug it into some math problem solver like Symbol Lab, which I think we can probably do. So let me see. Give me 1 second. Plus 49x. Yeah, no, I wouldn't give you this on the exam. That would just be pointless. Squared plus 1. Like the point of these questions is not to test whether you can solve system of equations. So I wouldn't do this. Okay, it didn't even work on Symbol Lab. It said no steps are supported for this problem. So I guess it was too long of a problem for even computational software to do. So yeah. I'll probably withdraw this question, to be honest. This is question 10, right? Yeah. So let me just make a note of that. Yeah, it does take forever. I mean, I have the answer right here in case you want to like jot it down. But from the answer, you can maybe deduct what A, B, C, and D were. So like 7/2. So that was probably what A or B was, and then 6/7. So you know that's probably has something to do with it. But yeah, that's that. All right, so let's go on to today's lesson. Okay. Um, oh yeah, there's the fail on Symbol Lab. Today we're talking about approximating integrals. So there are various methods of approximating integrals, um, 5 to be exact, 3 of which you guys have learned in Calc 1. So this will be part review and part new stuff. So what are the 5 methods of approximating integrals? Actually, there's 3, but the first method has like 3 sub-methods, so that's why there's technically 5. So the first method is called Riemann sum, which should sound familiar to you guys. Do you guys remember what Riemann sum is? Those of you who remember, what was that all about? This is a good topic.
It was about like finding areas under the curve based on like how big the intervals were. So basically,
Yeah,
you like squares, and you just find those.
yeah, pretty much. So yeah, Riemann sum is basically when you, well, spoiler alert. So, well, you should have known this, but the area underneath the curve is also the same as calculating the integral from one point to another point. So uh, there's 3 methods. Riemann sum is one method. Trapezoidal rule and Simpson's rule. Those should be new, so we'll go over those later. Um, here's an illustration. So consider the function x squared plus 1, which is this red line here, red curve. And then the area underneath the curve is shaded in green. So if I was to take the integral of x squared plus 1 from, say, x equals 0 to x equals 2, which is this green area here, that will give you the area of the green region. So it appears that not all functions are integratable, like able to be integrated. So in certain cases, you want to estimate integrals instead of doing them for real. So what are the methods of actually estimating that area? Riemann sum is one of those methods. So what does Riemann sum say? It says that you can actually split the area underneath the curve into many rectangles. And then if you calculate the area of all those rectangles and then add it all together, that's your estimate. Okay. You also learned that as you increase the number of rectangles underneath the curve for your approximation, then your estimate gets better and better. Like it gets closer to the true value of the integral. Yeah. So here's your illustration pictures. So just for review, we're going to do an example on how this worked. This is like Calc 1 stuff. So let's do this together. So consider the integral from 0 to 2 of x squared plus 1. We want to approximate the integral using Riemann sum. So there's 3 types. There's left endpoint, right endpoint, and midpoint. And then I specified that n equals 4. That's going to be the number of rectangles you use. So here we're specifying 4 rectangles. So let's see how this works. Screen, paste. Switch. Okay. So it's good to have a picture. So let's draw a picture. We only need the first quadrant because this is from x equals 0 to x equals 2. So this is just the positive x and y axis. X squared plus 1 is a parabola that's shifted up 1 unit. So it looks something like this. Okay. Then 0, 1, just put 1 over here. Let's put x equals 2 over here. Okay, so we are interested from 0 to 2. So let me cut off that region. This is x equals 2, and then here's x equals 0. So we're trying to find the area here. And because we're splitting it into 4 rectangles, let me section it off into 4 pieces. So here's 2 pieces, and then here's 4 pieces. Okay. Now the question is, when they say left endpoint, how does that look like? If you look at each of these sections, they're not rectangles yet, but you can make them rectangles by just making the top flat. So this is the first section right here. The height of the rectangle is going to be based off of the left side of the rectangle. So this is the left side, this is the right side. So starting from the left side, I'm going to just draw a straight line like this. And I'll do that for all the rectangles. Okay, so there's your rectangles based off of left endpoint. And then what we want to do is just find the area of all those rectangles and then add it together. So let's do that. The notation we used is usually the letter A with the subscript L for area left endpoint. And so what would be the, let's just do one rectangle at a time. So for the first rectangle, what's the length and the width? Or length and height, whatever.
Zero 0.5 and 1.
Yes. So can you explain how you got those two numbers?
Since there's 2 rectangles between 0 and 1, and we divided them equally in half, we have to do 1 divided by 2, which is 1/2. And we know that's the width. And the length is just the point on the y-axis, which is 1. So 1 and 0.5.
Yeah. So we know that this distance here is 0.5 because it's going from 0 to 2, and we're using 4. So we sort of just did like 2 minus 0 divided by 4. That gives you the width. So that's where the 0.5 comes from. And then how do we get the 1? So we're trying to figure out what this length here is, which is basically the, like how far it's going on the y-axis. So you just have to plug in x equals 0 into the equation here to get 0 squared plus 1, which is 1. So that's how tall the rectangle is. Yeah. So now that we know how to find the dimensions of all the rectangles, let's do all of them. So this is 0.5. All rectangles are the same width, right? They're all 0.5 because they're all equally spaced. And then this one here is this height, which is this value here is f of 0.5, right? Where f of x is x squared plus 1. So to find the y value, you just have to plug in the x value. Like for example, this is 0.5 for x. You just have to plug in this x value into the given equation here. So 0.5 gives you 1.25 as your height. And then the third rectangle is when you plug in 1, so that's a height of 2. And then the last rectangle is 0.5 times, and you plug in this x value, which is 1.5. So that's what is 1.5 squared plus 1? It's 2.25, so it's 3.25. Okay. So it's 3.25. Yeah, and then you just plug this onto a calculator. If you want to, you can factor out the 0.5 because that's common to all the rectangles. And you just have 1 plus 1.25 plus 2 plus 3.25. And this will give you the area of all 4 rectangles. So again, I don't know what this is. Maybe I could do it in my head. 5.25, 6, 6.5, 7, 3.5. Okay, so the approximation for the left endpoint Riemann sum is 3.5. Hopefully this is all coming back to you. Any questions about how I did all this? Okay, then let's go to the right endpoint. Delete. So we're still using 4 rectangles. So the length of each rectangle is still the same, it's still 0.5, but the height will be different. So let me draw the section again. Here's 1, here's 2, here's 3, here's 4. So instead of deciding the height of each rectangle from the left side, we're going to do it from the right side. So the first one, it's going to look like this, and then like this from the right side, from the right side. Okay, so the area using right endpoint is going to be 0.5. And then how would you find the first height? At this rectangle here.
You can plug in the x value into the original function.
Yeah, so we're going to plug in 0.5 now because that's how tall our rectangle is. It's the height when x is 0.5, which was 1.25. And then 0.5. Now we plug in 1, which gives us 2. 0.5. Plug in 1.25, which is this, plus 0.5 times, and then the last rectangle is this one right here, which the height is dictated by x equals 2. So that's 4 plus 1, that's 5. Okay, so this will give you the estimate for right endpoint. All right, what would this be? So it's someone on the calculator, they can just tell me out here. Let me see if I can do this. 3.25, 6.5.
5.75.
Thank you. So 5.75 would be your estimate. Okay, and then we had this conversation in calculus where you talk about which estimates are overestimates and then which estimates are underestimates. So for this example, what would it be? Left is under and right is over. Yeah, you can sort of tell from the picture as well. So when we draw the right endpoint, you see how the rectangles, they're sort of going over the function. So you can tell it's an overestimate. And then the left endpoints, the rectangles were underneath the blue line. So that was underestimate. Okay. And then the last one is midpoint. So that one is the same thing, except now the height of your rectangles are not dictated by either the left or right side, but the midpoint of the interval. So we used A sub M. We just use a different color. So they're going to be sort of like over here. Okay. So now the rectangles are like this. The first rectangle is going to be f of 0.25 now, because that's the midpoint between 0 and 0.5. .0625. So it's that plus 0.5. Yeah, I mean, you guys should be okay with this. I'm just going to write what the x values are because I don't feel like plugging all of them in. So this is f of 0.75. And then the third rectangle would be f of 1.25. And then the last rectangle, f of 1.75. Okay, and whatever this is will give you the estimate. All right. Is that okay? Like, do you guys all remember this now? Okay, and then as always, because this one is a relatively simple integral, we can always just, for reference, do the actual integral to get the actual value. So let's just see what it would be. Integrating would give you x to the third over 3 plus x, valued from 0 to 2. So this would be 8 over 3 plus 2 minus 0. So yeah, I don't know what that is. 6 over 3, which is 14 over 3. So this is the actual value of the definite integral, which should be close to these values or should be in between these values, which you can use as reference. Okay. All right. So that's our example. All right, back to the PowerPoint. So um, they did give you a formula for all this, which says that if you want to add up the areas of all the rectangles, you can use this one. So area of rectangles equals, this is delta of x times the summation of f of x. So delta of x is basically the length of each rectangle, right? Which in our case, in the previous example, was 0.5. And then summation of f of x, that's like the height of each rectangle. And then the x value depends on whether you're using left, right, or midpoint. All right. You guys should remember this formula. I remember when I first took calculus, they gave me this formula and I had no idea what it meant until I did an example. So yeah. Okay. All right, moving on to new stuff. So here is the trapezoidal rule. For Riemann sum, we split the area into many rectangles, but there's actually a better way to do the approximation. I'll give you a more accurate approximation, and that is to split the area into many trapezoids instead. So that's what the trapezoidal rule is all about. We're going to just look at how the formula works. So the area of a trapezoid, does anyone know the formula for the area of a trapezoid? Because I did not. I mean, I used to, but then I forgot. So apparently it was this. It's well, this is the formula if you were to do it on like an XY plane, but it's delta of x over 2 times the two bases of the trapezoid. So that's the formula for the area. And then if you were to like sum up a bunch of trapezoids, you would get the following formula on the bottom here. So there's many steps to this formula. Like if you want to see the proof, we're not going to go over it because I don't think any of you guys care. So we're just going to leave it at that. Copy down this formula and then we'll just talk about the features and how to use it. So let me just give you guys a second. Okay, so let's see how this thing looks like. So to approximate the integral using trapezoidal rule, we have delta of x over 2. So that part is the same as Riemann sum. And then let's see what's inside these brackets. So we have f of x0 plus 2f of x1 plus 2f of x2 plus dot 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 2f of x and minus 1 plus f of x of n. So basically what it's saying is you're going to add up all the x values, but you're going to multiply all the x values by 2 except for the first and last one. So that's how trapezoidal rule works. Okay. Any questions about this formula? We'll see an example later. All right. Before we do examples, we're also going to just cover the last rule. So here we have Simpson's rule. What is Simpson's rule? So instead of using rectangles or trapezoids, we can get an even more accurate approximation for the integral using quadratic functions. So if you look at this diagram here, and then you look at, say, the green part. So the first two intervals on the left, notice how the red line um, goes through the three x values, and then same with the yellow region, and then same with the blue region. So it always goes through the left one, the middle one, and the right one. And then because of that, you have basically like a bunch of quadratics. Okay. Here's the formula for Simpson's rule. So the formula for the area of each quadratic is just this. You don't need to know that. All you need to know is how to use this formula on the bottom. So I'm going to give you guys a moment to jot that down, and then we'll talk about it. Okay, so let's talk about this. So to approximate the integral, you have delta of x over 3. So that part's a little bit different than the other two rules. The other ones were were delta of x over 2. This one's delta of x over 3. And then in the brackets, we have, notice how the coefficients are 1, 4, 2, and then dot, 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 2, 4, and then 1. So how this works is the first and last y values are just multiplied by 1. And then you start with 4 for the second term, and you just alternate back and forth. So 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. One note about Simpson's rule is that if a question asks you to use Simpson's rule, it will always have an even number of subintervals. That's just to make sure that the second term and the second to last term are always 4, because it just has to be that way. So yeah, those are trapezoidal rule and Simpson's rule. Any comments before we move on to examples? Is L N? What is I N? Where's I? You mean the top one, the A of I part? Um, I is not N. I is just like, it's like a placeholder variable for like which subinterval you're looking at. So for example, if you're talking about just like Riemann sums, notice how we had 4 subintervals in our example. So then you would call the each region like A sub 1, A sub 2, A sub 3, A sub 4, or like the 1, 2, 3, and 4 is your I. Yeah, so I is not N. Okay, so here's the example. In fact, this is going to be the only example we're doing today because I think these questions don't really have much to it. Here we have an integral that we purposely chose because you can't integrate this one. So you have to approximate it using one of these methods. Okay, so let's do this one. So number one says to use the midpoint Riemann sum. So that one's not really new, but we can do it. Let's draw a picture. It's from 0 to 2 again, so I'll just draw the first quadrant of the x and y axis. From 0 to 1 to 2. E to the x squared. I honestly don't know how that looks like, so I'm just going to draw any random curve because it doesn't really matter. So there it is. And all of these questions specify 4 subintervals. So it's all going to be 1/2 again. Zero 0.5, 1.5. Okay, so number one, we're using the midpoint. So A of midpoint is equal to the area of the 4 rectangles, right, using midpoint. So I'm not going to draw it, but you guys can imagine. And by the way, regarding the formula that someone asked earlier about like the A of I part, so technically if you wanted to, you could just call each region their own separate area. So this would be like A of 1, A of 2, A of 3, and A of 4. And then each one has their own area. So this is 0.5. Because they're all the same, I'm just going to write it outside and then add all the y values. So for midpoint Riemann sum, what's your first x value that we're plugging into the equation? So if we let f of x equal e to the x squared. Yeah, 0.25 because that is the midpoint of the first interval. So I'll just write it like this. F of 0.25 plus f of, what's the next one? Yeah, 0.75. 25 and 1.75. Okay, so whatever this is will give you the integral approximation using midpoint Riemann sum. Okay, and then I actually have this pre-done, so let me just write down the answer that I got. So I got 14.48. Well, approximately. So that. All right. right, number 2 says to use the trapezoidal rule. So let me just pull up the formula real quick. Okay, so this is going to be equal to, first we have to do this part, which is delta x over 2. That's basically going to be the length of each trapezoid, which in this case is going to be 0.5 as well, because it's the same as the rectangle one. So this is 0.5. And then for the y values, because there's no left or right endpoint, you're actually going to use all the y values that you labeled. So this would be f of 0 plus f of 0.5. Forgot the 2. Hold on. Remember that all the middle terms have a 2 in front of it. So 2f of 0.5 plus 2f of 1 plus 2f of 1.5 plus, this is the last term, so we don't need a 2 anymore. So f of 2. By the way, in case you guys don't know the formula for delta of x, let me just include it again. So delta of x is basically b minus a over n. So in this case, our interval is from 0 to 2. So that's basically your a and your b. So this would just be 2 minus 0 over 4 subintervals, which is how we got 0.5 here. Oh, actually, I forgot to put the over 2 part. Sorry. Okay, so this is the coefficient, and then this is the longer part. All right. So that's trapezoidal rule. Any questions on that? You guys are all good on this? Is this like, do you guys find this simple? Because that's how I feel like whenever you guys don't ask questions. You learned this rule in Calc 1? Okay, yeah, I guess some Calc 1 teachers might teach it. Okay. Yeah, I mean, I don't think there's much to it besides like just using the formula. I mean, I don't give you guys the proof of this formula because like we said that we just omit those from the lessons. But if you're curious, they're on the internet. Like how is this formula derived and all that stuff. Okay, let's move on to the last question. So question number 3 says to use Simpson's rule. Okay. So here is formula. So we have delta of x over 3. So we know that delta of x is 0.5, and then we put that over 3. And then we're going to use the same x values, but the coefficients will be different. So the first coefficient is 1. So we have f of 0. The next coefficient is 4 times f of 0.5. And then it alternates. So 2, and then 4. 1.5. And then this is the last term, so it's going to go back to a coefficient of 1. So plus typo plus f of 2. Okay, so there's Simpson's rule. And then let me just write down the number I got when I did this before. So this turned out to be 17.353 when you plug all this into a calculator, which I forgot to write down the value for the previous one. So for a trapezoidal rule, I got 20.644. Some comments I want to make is that notice how n was 4 in this question. So 4 is even number, which means we can use Simpson's rule. And then you have the correct alternating coefficient. So it's 4, 2, 4, right? You always need to have like the 4s at the end, because if you had like an odd number of subintervals, that wouldn't really work out. You have like 4, 2, 4, 2, and then that would be wrong. Which answer is most accurate? I actually have the correct answer for the integral right here. So it's 16.4526. So I don't know which one's most accurate. Maybe the Simpson's rule. I don't know, I can't tell. Does their answer has to be the most accurate? No, it does not. Again, like for an exam question, I would just specify how many digits to round to. It looks like for this one, the trapezoidal rule was the least accurate because that was 20.6. But yeah, I mean, there's not a single rule that's always the most accurate. It depends on what type of curve you're given. So when that changes, then the most accurate rule changes. Can you see part 3? Yeah. As long as the answer is really close to the exact number, it should be fine. Yeah, I mean, these are all approximates to the integral. So like you're not going to get this number as your answer. You're going to get a number that's close to it. But when you calculate like this part in a calculator, I will specify what decimal place to round this answer off to. Okay, what is f, the original function? Yeah, so remember that we're trying to find the area of each subinterval, right? So for example, if we want to find the area of this subinterval here, it's going to be the length times the height. So the length was 0.5, and then the height is basically like the y value for this particular x value. So that's why I write f of 0.25, because this is your x value, and when you plug it into f, which is this equation, then that gives you the y value. So that gives you how high the area is. Okay. Any more questions? Can you go over which x values you should start off of with left and right Riemann sum? Yeah, I guess. So I'll just use a previous example from before. We were going from x equals 0 to x equals 2. And then we specified n equals 4. So that's 4 subintervals. So 1.5. So if you're using left Riemann sum, then your first x value is going to be the 0. So it's going to be f of 0. And then you're going to keep adding, and then your last x value for left endpoint is going to be f of 1.5. But if you do right endpoint, then your first x value is going to be f of 0.5, and then you keep adding all the way up to f of 2. Yeah. And this should be intuitively obvious if you just think about it in terms of like where do the heights of the rectangles come from? So if you draw like the right endpoint, you'll see that the height of the rectangle comes from the right side, which for the first value is the 0.05x value. But yeah, it's fine. I don't think any, let me see what the homework looks like for this section. Left, right, trapezoid, midpoint, Simpson's rule, Simpson's rule, Simpson's rule. Okay, so there's only 5 questions. All right, well, if there's no further questions, then that's all we have for today. So on your free time, please try homework 6.5. Yeah, which is really short. So yeah, that's it for today. You guys are free to leave. Have a good night, and I'll see you next Tuesday.